In this example, we're going to look at a different way of using probability tree diagrams. And in this example, we're going to be looking at events from two separate sample spaces, two different sample spaces. And what's also going to be different about this probability tree is that the different levels that we have aren't because we're choosing 1, 2, or 3 of something, but it's actually combining two different types of events together and trying to calculate a probability. And this example will also show one more attribute of probability tree diagrams that hasn't been discussed yet. So in the example, we're going to be looking at the probability of a disease test outcome. So in this example, 8% of people will develop a disease in their lifetime. So this isn't like in general, this is like a specific disease like lung cancer or pancreatic cancer or melanoma or something like that, any disease. Just imagine that there's an 8% chance of a person developing a specific disease. And so this means the probability of getting the disease is 8%. Now, a person with the disease has a 97% chance of a positive test result. So this means the probability of having a positive test result, given that the person has the disease, is 97%. A person without the disease, so that means not disease, has a 5% chance of a false positive test result. So what this means is the probability of a positive test result, given the person did not have the disease, is 5%. So what we want to try and determine is, given this information, what's the probability of a person being positive with this disease, a person getting a true positive test result, and getting a true negative test result. And so what we've got down here below is a probability tree diagram that's kind of already filled in. So let me try and explain how it was filled in. So starting here from this first node, this is whether the person has a disease or has no disease. And so we can see down this branch is the probability of a person not having a disease. And down the branch on the right is the probability of a person having the disease. So we were told in this problem that the probability of a person having a disease is 8%. So the probability of having this specific disease is 8%. But what we weren't told was what the probability is of not having the disease. And this kind of leads to another property of these tree diagrams, is that when you calculate the probabilities of both branches like this, those should add together to add up to 1 or 100%. So even though this branch on the left, the probability for having no disease is unknown, we can figure it out by just simply doing 1.00 minus 0.08, because these two probabilities should add up to 1. Either you have the disease or you don't, and that comes out to 0.92. So the probability of not having the disease is 0.92, or 92%. Okay, so that kind of represents the upper level. Now, down below, this is whether you either tested positive or negative, positive or negative. So here, down the left-hand side, if you didn't have the disease, you could test positive or you could test negative. if you did have the disease, you could test positive or you could test negative. Now let's I know this is really difficult to understand, but let's do this a little bit at a time. So let's say you did not have the disease, but you tested positive for it. This would be what's called a false positive. The test result said you were positive to the disease, but you in fact did not have it. That's a false positive. Now, what if you didn't have the disease and the test result was negative? Well, that is a true negative result. You didn't have the disease and you tested negative for it. So that is a true negative. Now on the right-hand side, let's say you did have the disease and you tested positive for the disease. Then that's what's called a true positive. And finally, if you have the disease and you took the test, but you tested negative for it, this is what's called a false negative. So when you set up the tree diagram this way, then you can look at the branches between each of these nodes. So if we look at the branch connecting no disease to positive, this would be the probability of being positive given you don't have the disease. This branch is the probability of being negative given you have no disease. This one is the probability of being positive given you did have the disease. And this probability is the probability of testing negative given you do have the disease. And so once you set up the tree diagram, you can see here, we know that the probability of being positive given that you're diseased is 97%. So we can look for, use a different color now. So we can look for this probability in our tree, and it's right here. So the probability of testing positive given that you have the disease is 97%. And because these two branches together have to add up to 1, then the probability of being negative given that you have the disease is going to be 3%, or 0.03. And here, at the top, a person without the disease has a 5% chance of a false positive. So that's the probability of a positive test result given you do not have the disease. So that is right here on this branch, the probability that you're positive given you don't have the disease, and that's 5%. So this other branch that goes with it, again, these have to add up to 1, should be 0.95 or 95%. So now we've got this tree diagram somewhat filled out. We're almost there. So let's calculate the probability here down this leftmost branch. So down this branch here. So the probability of a false positive. So that's going to be 0.92 times 0.05. And that'll be 0.046 or 4.6%. All right, let's look at this next one. So what's going to be the probability of having a true negative result? So that's going to be 0.92 times 0.95. So that comes out to 0.8740 or 87.40%. Okay, let's look at another one. So to calculate the probability of a true positive, so a true positive would be you have the disease and you tested positive for it. And so that's going to be 0.08 times 0.97. And that gives you 0.0776, which is 7.76%. And then lastly, the probability of having a false negative is going to be 0.08 times 0.03, which is equal to 0.0024, which is 0.24%. Okay, so we wanted to know what is the probability, let me get a different color. What was the probability of a positive test result? Well, we have a positive test result here, and we have a positive test result here. So that's going to be 4.6% plus 7.76%, which is equal to 12.36%. Okay, and B, the probability of a true positive. So the probability of a true positive is right here. We calculated that to be 7.76%. And then finally, part C, the probability of a true negative. Let's see, true negatives here. And that's 87.40%. So take a look at this. This says something interesting about disease tests. So even though a person with the disease has a 97% chance of a positive test result, you would think, well, if I got a positive test result, that means 97% I've got the disease because of this information here. And this is common with a lot of disease tests. But when you actually calculate the probability, what's the probability of having a true positive? Getting a positive test result and you have the disease, it's only 7.76%. So what that means is, even if you take a test for disease and you test positive, you want to take that test again. And that lays the foundation for what's called Bayes' theorem. And Bayes' theorem changes the probabilities with the more information that you get or the more tests that you take. But you're a little bit more in the clear if you get a true negative. So if we look here at a true negative, so a true negative is you don't have the disease and you tested negative for it. There's an 87.40% chance of that. So if you take a test and you tested negative, there's a really good chance, a really good probability that you don't have the disease.